All right, here we're reviewing systems of equations. Remember, we have three big methods for solving systems of equations. It's solving by graphing, solving by substitution, and solving by elimination. All right, graphing, obviously, we use a graph, and then we pull certain pieces from the graph to solve. Substitution and elimination are considered our algebraic methods, where we don't have a visual of the point that we're trying to find. We just find it by plugging certain things in and adding certain things together in order to solve the variables like we would any other equation. Okay, so if I look at this first couple, it says on a graph, the point of intersection is what we're looking for. So the solution to a system is where the two lines intersect. It's that one point that they share. It's that one point that they have in common. For example, if I look at something like this guy, again, I'm just going to graph each of these. And if I graph each of these, then I should be able to find the point that they have in common by looking for the point where the two lines cross, where they intersect. So this first one, this is in slope-intercept form. So that has a y-intercept of 1, so I plot the positive 1. And then it has a slope. Remember, this is the slope right here of a negative 1/2, which means I go down 1 over 1 from there. Sorry, I erased my point by accident. So down 1, over 2. Down 1 over 2, down 1 over 2. That's how I graph a slope of negative 1/2. I can keep going the other direction. And really, I technically only need 2 points in order to graph the line, but I want to make sure this thing is super accurate because I'm looking for a very specific point where these two intersect, okay? If I graph the second one, again, it's got a y-intercept here of 7 and a slope of 1. So I start up here at 7, 1, 2, right up here. And a slope of 1 would be like up 1 over 1 or down 1 back 1. And so again, I just graph this thing. And again, I want to graph it with an extreme amount of accuracy. I want to make sure that this thing is accurate, which is why I plot so many points. And now the solution is just where these two intersect. And I can see right here is where they intersect. So I identify that ordered pair. Looks like a negative 4, 3. And if I write that ordered pair down, negative 4, 3, that's my answer. And I can leave my answer as an ordered pair. From an algebraic perspective, this is telling me that x equals a negative 4 and y equals a 3. It's telling me what each variable equals, but it's giving it to me in terms of that visual piece of the ordered pair to say, hey, this is the point that they have in common. This is the 1xy combination that works for both equations in the system. Okay? If I look at this one, once again, I'm going to plot this first guy. In order to graph this first one, the best way to graph that first one, because it's in standard form, is I want to use my x and my y-intercept. Remember, to find the x-intercept, I plug a 0 in for y. So if I plug the 0 in here, and if we solve that in our head, we divide each side, I get x equals a 3. And that is not a solution to this system. It's not giving me the answer. I'm just using that to graph, and this is one of the reasons I always write this as an ordered pair. That's the ordered pair 3, 0. It's just there helping me graph. And I do the same thing. I plug a 0 in for x. And I solve that for y. That gives me a negative 6. But again, that's the ordered pair, 0, negative 6. Okay? I'm using those 2 points in order to graph this thing. That's how we graph lines in standard form. So now let me plot those 2 points. 3, 0, and 0, negative 6. And from there, I could try drawing a line to connect these two, but keep in mind, that's up 6 over 3, so the slope is up 6 over 3. That's a slope of 2. I can fill in the gaps in between here, okay? And again, the reason I want to fill in those gaps, I want this thing to be really accurate so that I can see the exact point of intersection, okay? And then the second line here, once again, it's got a y-intercept of 2, so I plot the 2. And then it's got a slope right here of negative 2, so that's down 2 over 1. Down 2 over 1, down 2 over 1. And, I continue to plot these points. I want this thing to be really accurate. As soon as I see where the point of intersection is, I really don't need anything else, but I wanted to draw some nice, accurate lines, and now I can see they intersect right here at the ordered pair 2, negative 2. And again, that's just a nice way of saying, hey, the one ordered pair, the one thing they have in common, the one x and y combination that works is when x equals 2 and y equals a negative 2. Okay, and I write that as an ordered pair. All right, getting on to our algebraic method. Instead of having to draw a graph each time, substitution is the first algebraic method we have. And with substitution, we isolate one of the variables. We get one of the variables by itself. And then we substitute that expression in, all right? We plug it into the other equation, and then we solve, okay? And so this is kind of a bare bones explanation of this, again, because we're just reviewing this, but isolate one of the variables so that I get x equals something or y equals something, and then I plug that something in for x or y into the next equation, okay? I substitute it in, and then I solve what's left. For example, if I look at something like this guy, and one of the things with substitution that we have to look out for is we always want to identify what's the easiest thing to get by itself. What's the easiest variable here to isolate? And so as I look around at this thing, like I have that x value, that y value, and x value, and I look around and just say, okay, which of these would be easiest to get alone? And hopefully you look at it and say, well, that x in the second equation is the obvious choice because it doesn't have any coefficients getting in the way. It's already got a coefficient 1. It's almost by itself. And so that's the one I want to isolate. So to isolate that x, I need to get rid of this 5y, and I do that by subtracting 5y. And so the second equation becomes this. It becomes x equals negative 5y and a minus 2. And so what happens here is I've isolated this variable, but it's basically saying, hey, x is the same thing as this, which means I can go to my other equation, and I can replace this x value with this thing right here. Okay? So I replace that x value with the negative 5y minus 2. And the whole point of doing this is when you replace x with an expression like we have, basically, instead of having an x and a y in the equation, now I just have y. I just have one variable, and we know how to solve when we only have one variable. This one, I'm going to do my distributive property. And now those two y's are on the same side of the equation, so I can combine like terms. So I can add those together. And now I can solve this thing. I work backwards through order of operations, so I'm going to undo the subtraction by adding 4 to each side. The plus 4 and minus 4 cancel. And now I can undo multiplying by negative 13 by dividing each side by negative 13. Again, the times 13 and divided by 13 cancel. So I'm left with y equals a negative 1. All right, but I'm not done yet. I have to plug that back in. I always take this equation down here, the one that says x equals, and I plug it into that guy. So let me plug the negative 1 in here for y. And now it's just a matter of simplifying. Sorry, I added an extra parenthesis there, like a crazy person. So x equals 3. So I've got x equals 3. I had y equals a negative 1. If you left it like this, that would be okay. I'm just going to write it as an ordered pair. All right? Because now it brings us back to that idea of, hey, this is the point that they have in common. It's the x and y combination that works. Okay? If I look at this one, once again, if I'm solving by substitution, I will want to look for the variable that's easiest to get alone. And when I look through here, you might look at this and say, well, this x would be pretty easy to get alone, but so would this y. I would choose the y value. And the reason I would choose the y on this one is because it's already positive. All right, I don't have to divide by a negative or anything like that. So I'm going to take this first equation. Let me write it down here. And I'm going to solve for y. I'm going to get the y by itself, so I have to add this x to each side. Okay? Because the plus x and minus x cancel each other out. I'm trying to get y by itself, so here it is. Y equals, I've got an x and a positive 1. So x plus 1. You could write it as 1 plus x. It doesn't matter. Either way is fine. But now I have an expression for y. If y equals this whole thing right here, if y is an x plus 1, I can go to this other equation. I can replace this y with an x plus 1. So that's what I do. So I replace the y with an x plus 1. And again, by doing that, I basically don't have x and y anymore. I just have x, and I know how to solve equations when there's just x. So I distribute the negative 2. I combine like terms. And now I can work through the order of operations backwards and start solving this thing. So I'm going to add the 2 to each side. That's how I undo the subtraction here. And now I can undo that multiplication with some division. So I get x equals a 5. Once again, I'm not done yet. I'm going to take this guy down here, the y equals x plus 1, and I still have to find the y value, so I have to plug the x back in. Okay? So I get y equals, looks like a 6. And again, if you wrote it as x equals 5 and y equals 6 and said, hey, that's my answer, that's fine. All right? But I'm going to write it as an ordered pair. It's a nice, succinct way of writing it. And again, it brings me back to that idea of the point of intersection, the xy combo that they have in common. All right? All right, elimination is our other algebraic method. Remember, elimination, the first thing we want to do is we want to line up like terms. We're going to get everything lined up. And for our purposes, we always say put it in standard form, put in that format of xy equals constant. All right, xy equals a number. But again, it's just trying to get everything lined up. I have to make sure everything's lined up so that I can add these equations together at some point. All right, so get everything lined up. We want to get opposites in front of one of our variables, so either in front of x or y. If x has a positive 2 in one equation, I want a negative 2 in the other equation. Or if I'm eliminating y, if y has a negative 10 in one equation, I need a positive 10 in the other equation, okay? So I line everything up, I get opposites in front of one of my variables, and I do that through multiplication. I might have to multiply the equation by something, all right? And then I add the equations together to eliminate, all right? So I line everything up, I get opposites, so that when I add them together, one of the variables cancels out, and then I solve what's left, okay? So again, line it up, get opposites with some multiplication, add the equations together to get rid of something, solve what's left. For example, if I look at something like this guy, when I look at this, I can see that the x's are lined up. See, the x's are lined up, but the y's aren't. See, the equal signs aren't lined up. And the y's aren't lined up. Everything's kind of all over the place. I have to put these in the same format, okay? And typically the format that we go to is standard form. Remember the ax plus by equals c. Essentially just x and y on the same side. And so when we look, this second equation is in that format, all right? But the first one's not. So I'm going to rewrite that first equation. Let me take it off to the side over here. And let's just get it in the same format. So I'm going to have to subtract the 2y from each side. I don't want the 2y over on that other side, so I get rid of it by subtracting 2y, and I do it to both sides. But then be careful. I don't want to write this as negative 2y plus 3x. I want to have it in the same format as this, which this has the x, then the y. And just look at the signs right here. The 3x is positive, so I'm going to write the 3x first. And then the minus 2y. And then equals over here. These guys canceled. I'm just left with a minus 4 or negative 4. Okay? So just make sure you get in the same format. So now, back over here, now that these are in the same format, I've got the 2x plus y equals 9. I now have the 3x minus 2y equals a negative 4. And now from here, so everything's lined up. See, x is lined up with x, the y's are lined up, the equals is lined up, and the number that's by itself is lined up. Everything is lined up. Now I want to get opposites. I want to get opposites in front of x or opposites in front of y. And so I just have to look at this and ask myself, okay, is it easy to make a 2 and a 3 the same number or the opposite number? Or would it be easier to take this guy right here, the 1y and the negative 2y, and make them opposites, okay? And remember, we want to multiply to make opposites, and hopefully you look at this and go, okay, the y's are going to be easier because all I have to do to get opposites is I just have to multiply this first equation, that first y value, by 2. See, if I multiply that first equation by 2, I'm going to get a 2y, which will be the opposite of a negative 2y. And so I just have to multiply everything by 2. That gives me a 4x plus 2y equals 18. So I'm just rewriting that equation down here. But now everything's lined up and I have opposites, which means I can add these two equations together. Okay? The 3x, and again, let me kind of section that off. The 3x plus the 4x gives me a 7x. Right here, the minus 2y and the plus 2y, these cancel out. That's kind of the point. That's what we were trying to do this whole time, is we wanted to line everything up and get opposites so that when I add these together, they cancel out. And then the equal sign just kind of tags along for the ride. And now over here, negative 4 plus 18 is a 14. Okay? And then from here, I can solve for x. I divide each side by 7. So I find out that x equals a 2. All right. I'm still not done yet, though. I still have to plug this thing back in, and I can use any one of the equations. maybe I'll take the second equation, the 2x plus y equals 9. And I just have to plug that 2 in for x and then solve for y. And so to solve this one for y, I'm going to have to subtract that 4 from each side. Again, the plus 4 and minus 4 cancel out. So I get y equals a 5. And once again, I could leave it like this, as x equals this and y equals this. I'm going to write it as an ordered pair 2, 5. Okay? If I look at the next one here, again, I want to get everything lined up, which it already is this time. Look at this. The x's are lined up, the y's are lined up, the equals is lined up, and the constant is lined up. Everything's lined up. It's in the right format, so now I just need to get opposites. Okay? And you can get opposites in front of x or y. And really, when you're getting opposites, it's the same process you go through as finding the common denominator, all right? It's the idea of that least common multiple. What can I multiply each of these by to get the same number? And so I look at this, and maybe I want to go with something like the x's and say, okay, what number can I get to from a 3 and a 2? I want to multiply by something and get each of those to the same number. And the answer here is I want to get each of them to a 6. I want to turn this top 3 into a 6. And I do that by multiplying by 2. And so I want to turn the bottom number, the bottom x value, also into a 6, and so I have to multiply by 3. But now, right here, I'm about to get a 6 for each of them. I want a negative 6 for one of them. So just change this. Do a negative 3 down here. Okay? So we just multiply by a value that gives us the opposite instead. And so here's my new equations. That top equation, as I distribute the 2, that's a 6x minus 4y equals 14. That second equation, as I multiply everything by the negative 3, gives me a negative 6x, a minus 15y, and over here I get a positive 24. And so now I have opposites, everything's lined up. I can add these equations together, so I'm going to add them up. Again, the minus 6 and the plus 6 cancel out, so the x's kind of disappear. Right here, negative 4 plus a negative 15 is a negative 19y. And then over here, when I add these guys together, that gives me a 38. But now I can continue to solve what's left. I divide each side by a negative 19. Times 19 and divided by 19 cancel, so I get y equals, looks like a negative 2. All right? And once again, I'm not done yet. I have to take any one of the equations that I've used so far, and I have to plug this back in. I'm just going to take this... the 2x plus 5y equals a negative 8. I'm going to take that equation, and I'm going to plug the y value in. And so I simplify a little bit. That's a negative 10. And now I can solve this thing. I solve by undoing going backwards to order of operations and undoing the operations as I go. So I'm going to add 10 to each side. Plus 10 and minus 10 cancel. And now I divide each side by 2. Again, the times 2 and divided by 2 cancel. So I get x equals a 1. And once again, I could leave it as x equals this, y equals this. I'm going to write it as an ordered pair. It's a nice, succinct way of writing it. 1, negative 2. It's that one ordered pair. It's that one xy combination that they have in common. Okay? So solving systems of equations, you're looking for the xy combination that they have in common. All right? From the perspective of graphing, it's the point that they share. It's the point of intersection. All right? It's that one point that they have in common. From the perspective of solving it algebraically, we can do it through substitution, which is where we isolate a variable, plug that new expression into the other equation, and solve for what I have. All right? Or elimination, where we line everything up, we get opposites, we add them together, and solve for what we have. All right? We're finding one variable at a time when we solve it algebraically. All right? But we're still coming up with that ordered pair, that point of intersection, that one point that they have in common. Okay?